Hello everyone, very good evening. I welcome you all at India's most comprehensive preparation platform for all competitive exams, that is BYJU'S Exam Prep. So guys, in this session, we are going to discuss the important properties which you must ensure while you are normalizing the relation, means while you are decomposing a relational schema into sub-relations. So that's what we are going to discuss. So this is a brief introduction of myself. My name is Vishal Ravatia. I have 10 plus years of teaching experience, achievements and areas of expertise. Apart from that, for all of you, there's an announcement that Richa Gupta ma'am is going to conduct a workshop on 27 June at 7:30 p.m. In that particular workshop, ma'am is going to discuss the strategy that how you can reach in the top 1% in GATE 2024. So kindly enroll for this workshop. This is absolutely free. Enroll for this workshop and get benefited. Okay, so let's try to understand the concept. So normalization, we have already discussed this particular thing, that what happens, we try to decompose a relation into sub-relations so that we can eliminate the redundancy and we can overcome some of the anomalies, that is insertion, deletion and updation anomaly. Now, properties of decomposition. So we actually need to decompose the relation for the normalization. So a relation is decomposed into multiple relations if the decomposition satisfies the following property. So when do we decompose a given relation into sub-relations? When it satisfies these two properties. One is dependency preservation, another is a lossless join. So that's the two things which your relation must preserve when we are decomposing a given relation into sub-relation. So let's try to understand what do I mean when I say decomposition. So let's say if there is a relation R with FD set F. There is a relation R with FD set F, and now we want to decompose this relation R into two sub-relations. One is R1, another is R2. So this is relation R1, this is relation R2. So we are decompose. Now for R1 we will have one FD set, for R2 we will have another FD set. So let's say R1 with FD set F1, let me call the FD set as F1, and R2 is another sub-relation with FD set F2. Now what's the idea? See, we have already discussed the concept of join in the relational algebra lecture. So now we'll just discuss that in general, what are the properties? In general, if you perform the natural join of R1 with relation R2, then this natural join will be superset or equals to relation R, right? Now, if first, what's the property? If the natural join of R1 and R2 is a superset of R, then we say lossy decomposition. Right? Second, if this natural join is equal to the original relation R, sir, there is a confusion. You will say, sir, something extra is there. So why lossy? The loss of information, I mean, that's basically not consistent, right? Earlier, something was not available in the original relation R. Because of that natural join, that information is incorporated in the relation R. So from where exactly that information is coming in the relation R? So it's basically inconsistency. So the natural join of R1 and R2 is equals to R, then we say lossless joint decomposition. So the very first thing which we need to preserve is that if we are decomposing a relation R into sub-relations, then that sub-relation should be of the type that if we join those two relations R1 and R2, then we should get exactly the original relation R. So that's one thing. What's the next thing? So what is the information with respect to FD side? So second, in general, when you perform the decomposition, then the FDs which are present in the FD set F1, if you take the union of those FDs with the FDs which are present in the FD set F2. So let's try to understand. I have given you the concept that if we have a relation R with attributes A, B, C, D, and if we define a relation R1 with attributes B, C, D, or whatever, then the FDs of this subrelation R1 will eventually come the FDs of this set, FDs of the original relation R, right? So whichever FD comes in this subrelation R1 are actually from this FD set F. So there are some FDs of F which are coming in this set F1. There are some FDs of F which are coming in this set F2 based on the attributes of R1 and R2. So in general, what will happen? In general, the union of these two FD sets will be subset or equals to the original FD set F. Now, first, if F1 union F2 is a proper subset of F, means we have eventually lost some of the FDs. No Richard, this is for computer science engineers. This is a topic of database management system, right? So this is obviously not for electrical engineering. Okay, so if F1 union F2 is a proper subset of F, proper means you are missing something out of F. So if you are missing something out of F, then you have lost some of the dependencies. So if F1 union F2 is a proper subset of F, then not dependency preserving. Not dependency preserving. Second, if they are equal, if F1 union F2 is exactly equal to your FD set F, means you could preserve all the FDs of original FD set F, then dependency preserving. So what's the idea? If you are decomposing a relation R into two subrelations R1 and R2, then first this second term should be followed, that the natural join of R1 and R2 should be exactly equals to the original relation R, and the FDs, the union of the FDs of relation R1 and the FDs of relation R2 should result in the FDs of original relation R. So if these two properties are satisfied, then we say that the decomposition is correct, that it is dependency preserving as well as lossless join decomposition. So these two properties must be preserved. These two properties must be preserved. So now what you need to understand, sir, is it ever possible that the natural join of R1 and R2 is a proper subset of R? No, sir, it is not possible. So, note what you can remember, that R1 natural join R2 is a subset of R, not possible. Similarly, F1 union F2 is a superset of the FD set F, not possible. Why? Because we have already said the FDs of F1 are derived from this FD set F. The FDs of F2 are also derived from FD set F. So we cannot have any FD in the union of these two FD sets which is not present in the original FD set F. So therefore, F1 union F2 can never be a proper superset of F. So this is also not possible. So these are the things. This clears everything related to decomposition. So fine. So sir, what are we going to discuss in the today's session? So we are not going to discuss this particular thing, that is the concept of natural join in today's session, because tomorrow we will be discussing only about join. Tomorrow's session is only with respect to join. Today we will try to understand that if we decompose a relation into subrelations, then how do we determine the FDs of the subrelation, and how do we check whether the decomposition is dependency preserving or not. Now, first of all, let me give you the general definition for these two things. So, dependency preserving decomposition. What do I mean when I say dependency preserving decomposition? If you decompose a relation R into sub-relations R1, R2, R3 such that FD sets of R1, R2, R3 are F1, F2, F3, F2, Fn respectively, then for this decomposition to be called dependency preserving decomposition, what's the idea? The union of all the FD sets of sub-relation must be equals to F. So, earlier I have explained only in context of two sub-relations of a relation R, but no matter how many sub-relations you create for a given relation R, the union of FD sets of all those sub-relations should be eventually equal to the original FD set F for the decomposition to be called dependency preserving decomposition. That's one thing. Similarly, for lossless joint decomposition, if we decompose a relation R into multiple sub-relations R1, R2, R3, up to Rn, then the natural join of all those sub-relations should be exactly equal to R. If there is any extra tuple in this natural join of R1, R2, R3 up to Rn, then the overall thing will become lossy. Overall thing will become lossy. You cannot have any extra tuple in the natural join of all these sub-relations compared to the tuples of relation R. So that's it. So we are not going to discuss lossless joint decomposition in the today's session. Tomorrow we will discuss that this lossless joint decomposition is actually commutative, associative, so order and everything we will discuss in the tomorrow session. For time being, let's try to understand dependency preserving decomposition. So let's look at this example. Look at this example and try to solve this. I'm giving you 2-3 minutes. Just try to solve this question. This check. Consider a relational schema R which consists of 4 attributes A, B, C, D, and the FDs are A implies B, B implies C, C implies D, and D implies A. Now, if this relation R with attributes A, B, C, D is decomposed into sub-relations, one is R1 which consists of only 2 attributes AB, another is R2 which consists of only 2 attributes BC, and one is R3 which consists of 2 attributes CD, then this decomposition is dependency preserving or not? That's what being asked in this particular question. Check. Take 1 minute time and think. So to check that whether it is dependency preserving or not, first of all, we need to identify the FD sets of this subrelation R1, R2 and R3. So what will happen? See, this is a relation R with attributes A, B, C, D. FD set of this relation is as given. A implies B, B implies C, C implies D, and D implies A. These are the FDs. Now, it is being told that this relation R is decomposed into 3 sub-relations. One is R1, another is R2, another is R3. So, R1 consists of 2 attributes A and B. R2 consists of 2 attributes B and C. Similarly, R3 consists of 2 attributes, again not 3, C and D. But what we don't know is that what is the FD set F1 with respect to this relation R1, what is the FD set F2 with respect to relation R2, and what is FD set F3 with respect to relation R3. So how do we determine this? So I have already explained in the previous session that how do we determine the FD sets of subrelation. So what you need to understand? So there are two attributes A and B. So one thing, you will calculate A closer with respect to this FD set F. So what comes in the A closer? So the attributes which are available in the A closer with respect to this FD set will be A, B, C, D. Right? A, B, C, D. So what does it mean? That A is capable of determining what A is capable of determining A as well as B as well as C as well as D. But here what you need to understand, sir, in a FD set of a given relation, in the FD set of a given relation, we will only have the attributes which are part of that relation. Therefore, we don't need to worry about these two things C and D. Why? Because not in R1. Not in R1. Similarly, we don't need to worry about this A as well. Why? Because it is trivial. So what did we learn from here? That, sir, with respect to this A closer, we can say one thing, that A can determine B in this subrelation R1. Right? Similarly, you will try to calculate the closure of B. So what will be B closure with respect to FD set F, that what all could be determined from attribute B in the original FD set F. So F can give you the information of B, from B to C, C from C to D, D, and from D to A. Therefore, B implies A from here. B implies A is also present in this subrelation R1. Now you might say that, sir, you just told us that something, the FDs which are not present in the original relation F cannot be a part of F1. So here you are trying to say that FD set F1 will consist of two FDs, A implies B and B implies A. Then in the original FD set, B implies A is not directly available. So how are you saying that this B implies A may be present in the FD set F1? So you just need to understand that not all the FDs need to be represented in the FD set explicitly. There are certain things which can be implied from the FD set. So you can eventually see B to C and C to D, therefore B to D. Now B to D and D to A, therefore B to A. So B to A is present in this FD set F with the help of transitivity, though we are not writing it directly, but whenever we compute the closure, we will get that information. Got the idea? So B implies A is a part of this. Similarly, when you will try to compute the FD set F2, you will eventually come to know that B closure will contain all the attributes. Therefore, yes, B implies C will be a part of FD set F2. Similarly, C to D and D to A, therefore C to A. Now, C to A and A to B, therefore C to B. Therefore, C to B is also present in this FD set F2. Similarly, what will be FD set F3? Sir, FD set F3 will be C to D. Obviously directly available. Now D to A and A to B, therefore D to B, D to B and B to C, therefore D to C. So this is the FD. Now tell me, what is F1 union, F2 union, F3? Now what you need to do? Sir, F1 union, F2 union, F3 is what? Sir, F1 union, F2 union, F3 is A implies B and B implies A. Similarly, B implies C and C implies B. Similarly, C implies D and D implies C. So this is the union of F1, F2 and F3. Now to check whether dependency preserving or not, what you actually need to check. So your check F1 union F2 union F3 is actual equals to F or not. So what's the idea? So to say, what do we know? F is equals to G, F equals to G if and only if when F is the subset or equals to G and G is the subset or equals to F. Yes or no? to say that two FD sets F and G are equal, you just need to ensure that F is a subset of G and G is a subset of F. If both of them are true, then F is equals to G. So here you actually need to check what? So that is check F1 union F2 union F3 is a subset or equals to F, and F is a subset or equals to F1 union F2 union F3. Now one thing what you need to understand is that, sir, this FDs of F1, F2 and F3 are derived from this FD set F only. The FDs of F1, F2 and F3 are derived from this FD set F only. Therefore, this thing will always be true. You don't need to check for this. This is always true. You don't need to check for this. You only need to check whether F is a subset of F1 union F2 union F3 or not. What do you mean when you say F is a subset of F1 union F2 union F3 or not? So, all the FDs of F, all the FDs of F are in F1 union F2 union F3 or not. So what did we learn? Sir, let's check for the FDs of F. So A implies B. Is A implies B present in F1 union F2 union F3? Yes, sir. A implies B is directly present in F1 union F2 union F3. What about B implies C? B implies C is also present in F1 union F2 union F3. C implies D. Yes, sir. C implies D is also present in F1 union F2 union F3. Right? Yes. So what about D implies A? What about D implies A? Whether D implies A is present in F1 union F2 union F3 or not. That's what I'm asking. That's my question. That whether D implies A is also preserved after this decomposition or not. D implies A is preserved with respect to decomposition R1, R2, R3 or not. Tell me fast. Yes. So that's the idea. You may say, sir, that D implies A is not directly available in F1 union F2 union F3. You may say that D implies A is not directly available in F1 union F2 union F3 or F3. But you need to check what? D implies. So we are actually looking that check if D implies A is a membership property. Check if D implies A is a member of F1 union F2 union F3 or not. So how do we check whether X is a member of FD set F or not? So to check X implies Y is a member of FD set F or not, we compute the X closure with FD set F. So here we will calculate D closure with respect to F1 union F2 union F3. What is D closure with respect to F1 union F2 union F3? Sir, D closure will be D. From D to C, you will calculate C. Because of C to B, you will also get B. And because of B to A, you will also get A. Now, let's try to understand whether A belongs to the closure of D or not. A belongs to closure of D, therefore D implies A is a member of F1 union F2 union F3. So the moment you are saying that D implies A is a member of F1 union F2 union F3, therefore D implies A is present in F1 union F2 union F3. So you can actually see that all the FDs are present in F1 union F2 union F3. Therefore, I don't have sufficient space. I guess I can write here. Therefore, F from here, I'm saying all the FDs are present in F1 union F2 union F3, therefore F is equals to F1 union F2 union F3. And because F is equals to F1 union F2 union F3, therefore dependency preserving. Got the idea? So I have explained the complete process. I have explained the complete process that what you need to do. No matter what is the question, if there is a relation R, if there is a relation R and an FD set F, and the relation R is being decomposed into number of sub-relations, then you always need to do one thing. That first of all, you need to identify the FD sets of those sub-relations. Yes, how to obtain that? So FD sets of sub-relation will be calculated with respect to FD set of original relation. Fine, sir. So once you have obtained the FD sets of all these sub-relations, just have the union of all those FDs, and then check whether the union of all the FD set contains all the FDs of relation of all the FDs of FD set F or not, because you don't need to check whether F contains all the FDs of F1 union F2 up to union Fn or not, because all those FD sets F1, F2, Fn are derived from F only. So it is guaranteed that FD set F will imply the F1 union F2 union F3 up to Fn, but you only need to check whether F1 union F2 union F3 up to Fn imply all the FDs of FD set F or not. So that's the only thing. So once you are done with the union, just check that all the FDs of FD set F are member of that union or not. So if all the FDs of original FD set F are member of that union, then we say that the decomposition is dependency preserving. If any of the FD of the original FD set F, if any of the FD of original FD set F is not a member of F1 union F2 union F3 or the union, then you can actually say that the decomposition is not a dependency preserving decomposition. Do we need to solve multiple examples of the on the same concept? No, sir. Do we need to solve multiple examples with respect to same concept? No. We have understood the complete thing, that if we want to check whether the decomposition is dependency preserving or not, then we just need to ensure that after the decomposition, those different FD sets of subrelation are able to preserve all the FDs of original FD set F or not. That's the only thing which we need to understand. So that's the idea. So two properties: lossless joint decomposition and dependency preserving decomposition. Those two must be satisfied for a decomposition to be correct. So one thing we have understood in this particular session, that how to check whether the decomposition is dependency preserving or not. Please, if you don't know the concept of join, then watch the video which in which I have discussed the concepts of relational algebra. I have discussed the concept of relational algebra, in which I have explained that join is a derived operation which is derived using cross product of two relations R and S. Then you will have the selection from those from that R and X based on the equality condition on the common attributes of R and S, and then finally you will project the distinct attributes of R and S, and that will define the join or natural join of R and S. So once you have understood the concept of natural join, in the tomorrow's session we will see that what are the different types of join and how do we ensure that the decomposition of a relation R into sub-relation is a lossless joint decomposition or not. So that's what we'll see in the tomorrow's session. For today, this is it. So let's keep this one comparatively shorter session. So this is it. Okay, yes, there's an announcement that at 9:15 I'm going to discuss the concept of tuple relational calculus. I'm going to discuss the concept of tuple relational calculus. This thing will eventually involve the knowledge of predicate logic. Why? Because there exists for all if then all those things can be used in the tuple relational calculus. So we are going to discuss the tuple relational calculus. Obviously, we will not discuss the concept of predicate logic in this particular session, because I'll believe that you know the concept of predicate logic, because I've already discussed the concept of predicate logic on the app, and those classes are free app classes. So if you don't know the concept of proposition logic and predicate logic, then you can first learn the concept of proposition logic and predicate logic from those free app classes, and then you can try to understand the concept of tuple relational calculus. But this session will be conducted at 9:15 p.m. followed by a practice session on tuple relational calculus, and that practice session will be at 10:15 p.m. So this is on app. This particular session will be on app, free app class. This is a free app class. Anybody can join this. But yes, this session will be on app. So this is it for this particular session. Thank you very much. If you like the concept, then please hit the like button. If you are new to the channel, then kindly subscribe for the channel and press the bell icon to get the notification about our upcoming video. Thank you very much. See you in the next session. Till then, take care. Bye bye.